So let's begin here. So I realized on your exam that I actually gave you something that I hadn't gotten to in class last Thursday. And so I won't dock you points for not getting this exactly right. And if you read further in the book and did get it exactly right, I'll give you a bonus point. And that was to deal with a situation where you're doing hypothesis testing on a mean when the population variance is unknown. Okay, and that did come up on an exam problem. Let's see, right, this problem here about the Teflon steel. You really do need to use a t distribution instead of z. Have your attention, please. You really do need to use a t distribution instead of a z. So if you use the t, I'll give you a bonus point. If you use the z, I won't dock you points. Okay, so it's just like with the confidence interval. When the population variance and standard deviation are not known, and you're talking about either doing a confidence interval for a mean or hypothesis test for a mean, you should use a t distribution. Let's work through an example of that to start with today. This problem, number 37 in chapter 8. Ozone is a component of smog that can injure sensitive plants even at low levels. So that sounds bad. Of course, actually, ozone has good aspects about it. Have you heard about the ozone layer or ozone holes in the atmosphere? Ozone does protect us in the upper atmosphere against, I think, ultraviolet rays from the sun. They'd be a lot more harsh if the ozone layer wasn't there. But when it's near the ground level, then it's a component of smog, and it can make breathing difficult, and it can evidently injure plants. In 1979, a federal ozone standard was set at 0.12 parts per million. ppm means parts per million. It's thought that the ozone level in air currents over New England exceeds this level. To verify this contention, air samples are obtained from 30 monitoring stations set up across the region. Okay. So the background here is you've got this theory. You think in New England that ozone level is too high. You think that if you measured the ozone level at every location, say, the mean of that population of locations would be above 0.12 parts per million. That's telling you the alternative hypothesis should be that mu is bigger than 0.12. A right-tailed test, as we've always been doing in class, on the exam you were doing a left-tailed test. Part A does set up appropriate, it does say to set up appropriate null and alternative hypotheses to verify this contention. Let's go ahead and start that. And again, oftentimes we're not extra picky about actually stating the meaning of the population parameters. They don't say to do that here. And I don't always require it on tests or on homework, but really in reality, you should. Chapter 8, number 37. Mu is a population parameter. It's good to keep that in your mind. That's the thing you're trying to test. It's unknown. Nobody knows it except God. Okay? You'd like to know something about it. You'd like to do inference based on a random sample. You'd like to say something about it. In this case, perhaps reject a null hypothesis or fail to reject the null hypothesis. This would be the mean ozone level in New England. In parts per million, ppm. If you wanted to be a little bit more precise, maybe you'd say it's the mean ozone level at every single location in New England. Like if you could measure this at every single square meter of land, I don't know, 5 feet above the ground or something, that would be your population. And the mean of those numbers would be the population parameter that you're trying to do inference about. Again, state the alternative hypothesis first. They think that it's bigger than 0.12. So this is a right-tailed test. As, like I said, all the examples we've been doing so far have been right-tailed tests. The null hypothesis is the opposite. Technically speaking, that would be mu is less than or equal to 0.12. However, as I've emphasized, we always write it as an equal sign, even though technically speaking, it's less than or equal to 0.12. The reason is because when you do the test, when you calculate the p-value, for example, you assume the null is true, and it's simplest to go ahead and assume it takes on the boundary value. It's also sufficient to assume it takes on the boundary value because it turns out any p-value you'd obtain for this boundary value is going to be bigger than a p-value you'd obtain from some other value like 0.11 or something. And why is that a good thing? That's a good thing because you want to make it, even though you might like to reject the null, you want to make it hard on yourself. You want strong evidence before you do because you don't want to make a type 1 error. So by making the p-value as big as possible, you might say, by taking the boundary value of the null hypothesis, you're making it harder on yourself to reject the null. You're going to require stronger evidence before you reject the null. As we do the calculation, maybe I'll mention that again. So that's the setup. That is part A here. Part B says, what is the critical point for a 0.01 level test based on a sample of size 30? Okay, that's not a p-value here. And the directions here don't say to find a p-value, it looks like, though we could. Critical point means boundary of the critical region, rejection region. I'm using critical region and rejection region synonymously. 0.01 level, that means that alpha is 0.01. You're trying to design the test, design the rejection region so that your probability of a type 1 error is 1%. It's easiest to do this either in terms of Z or T first. We don't know the population variance or population standard deviation. We've got a sample standard deviation. So technically speaking, what this ends up meaning is I need to use a T distribution with a certain number of degrees of freedom. And the degrees of freedom is the sample size minus 1 in this context. The degrees of freedom will not always be the sample size minus 1. In this simplest of contexts where we have to deal with degrees of freedom, when you've got one population and a sample mean to study a population mean, then the degrees of freedom is n minus 1. But in some other situations, including regression, also including in chapter 10, comparing two means from two populations, the degrees of freedom will not be n minus 1. Okay, just in the simplest situation. So what's the critical point of a 0.01 test based on a sample of size 30? What I should do first is I should think about a T distribution with 29 degrees of freedom. And what is the critical point? I need the table for a T distribution or my calculator. I'll do it both ways. Here's the T distribution. Gamma is the degrees of freedom. Looking for 29 degrees of freedom. Remember that these numbers, by the shading here and by the less than or equal to here, these are CDF values, areas to the left. If alpha is 0.01, that means I'm looking for 0.99, 1 minus alpha. Going down to 29 degrees of freedom, it means the critical value is 2.462 right there. 2.462. So yeah, with n equal to 30, that means the degrees of freedom, df, or if you prefer gamma, is n minus 1 is 29. Alpha is 0.01. We are doing a right-tailed test, and it's not a confidence interval. We do not have to divide alpha by 2. We divided alpha by 2 for confidence intervals. And we might have to divide alpha by 2 when we're thinking about two-tailed tests, which we really haven't done yet. I'm really looking for t sub 0.01. And remember, like I said in the table, that means that the area to the left is 0.99. And what we saw is it's 2.462. That's the critical value of the rejection region in terms of t. I could also try to figure out the critical value of the rejection region in terms of x bar if I wanted. Maybe I will do that, even though it's not technically required for the problem, just to try to make sure we understand it all. You're going to reject the null if the t statistic is bigger than or equal to 2.462. That's what this means. In terms of a t distribution with 29 degrees of freedom, call it capital T sub 29, this number has the property that this area is 0.01, and you reject the null if the observed value of the t statistic is that extreme or more extreme. Observed values of t statistics to the right of this correspond to p-values less than 0.01. This is the alpha. If we get a t statistic bigger than or equal to this, that means the p-value is less than 0.01, and that does lead to rejection, even though this problem doesn't talk about the p-value. Let's leave it like this for the moment. Move on to part C. When the data are analyzed, a sample mean of x bar equaling 0.135 is obtained and a sample standard deviation, S, not sigma, S, 0.03 are obtained. Use these data to test the null. Can it be rejected at the 1.01 level, 1% level? What does this mean? What does your decision to reject the null or not mean? Okay, write these numbers down. X bar. The observed value of x bar, so I'll make it a lowercase, is 0.135. That is larger than the null value, right? This is what I'm about to say is the crux of the issue here. X bar, the sample mean, is definitely larger than the null value. It seems like we've got some evidence against the null. The question, the issue is it statistically significant evidence against the null? Is it unlikely to have occurred by chance if the null is true? That's the issue. That's always the issue in this context. Have we observed something rare if the null is true? If we've observed something rare, something extreme, when the null is assumed to be true, then we say, well, we think the null is wrong, and we reject it. S was 0.03, is that right? Now let's find the corresponding t statistic. The way you find the t statistic is the same kind of way you find the z statistic, except you use s instead of sigma. You essentially are standardizing x bar minus the null value of mu, call it mu sub 0, divided by s over square root of n. That's the same thing we called z before when we used a sigma there instead of an s. Before, we were essentially standardizing capital X bar, assuming we knew its sampling distribution, which would be, by the cornerstone theorem, exactly normal when the population's normal, and you might say approximately normal when the population's approximately normal. And the central limit theorem can come in there as well. But now when we replace sigma with s, statisticians have found we get a little bit more accuracy by using t distribution, calling this t instead of z, with 29 degrees of freedom. So for this problem, this is 0.135 minus mu 0 is the null value, the boundary there, 0.12, divided by s over square root of n, n is 30. So we get 0.015 divided by 0.03 divided by square root of 30. This number here, 0.005477. What does this number represent? It's s over square root of n. It's really an approximation, an observed estimate for sigma over square root of n, which would be the standard deviation of the sampling distribution of x bar. It is an observed value of the statistic. If we took a different sample, we'd get a different answer. Even if n is still 30, right? We still probably wouldn't get s to be 0.03. We'd probably get it to be something slightly different. And we get a slightly different answer here. Using a t distribution sort of intuitively takes that variability into account. Anyway, take 0.1015 and divide by this, and we get about 2.739. That is in the rejection region. We reject the null. Therefore, reject the null. Right, this is extreme. We have observed an extreme t statistic. Extreme enough to be in the rejection or, again, critical region. People use both terms. The corresponding p-value is going to be less than 0.01. I haven't actually calculated the p-value here. By the way, I was going to confirm this number, 2.462, with the calculator as well. Instead of the table, if we go to the distributions menu and use inf t, that would be what to use to confirm this number, 2.462. Inf t, that subscript 0.01, so the area to the left is 0.99, degrees of freedom is 29. 2.462, yep. I did describe the rejection region in terms of t. I could have described it in terms of x bar as well. Notice I am assuming the null is true when I do this calculation. Remember, the null is like the innocence. You give the null the benefit of the doubt. You assume it's true when you do these calculations. Just like a defendant is assumed to be innocent until proven guilty. If we were going to figure out the rejection region in terms of x bar, it's essentially a matter of, well, let me use capital X bar. Well, okay, this is a little bit not so good. The way we did it is the best way. I would have to use a specific value of S if I wanted to actually have a fixed rejection region in terms of X bar. So I'd have to actually use the observed value of S. Essentially, I'd have to solve this inequality for X bar, assuming that S is 0.03. That's maybe not the best thing to do because for a different sample, S would be different. So while you could do that, it would not be the same for a different sample, and so that's not ideal. But let me just cross that off. It's best to do in terms of T. What about the p-value? We're not asked for the p-value here. Well, maybe we should answer the question still here. So we reject the null. Yes, it can be rejected at the 0.01 level. What does this mean in a practical sense? It means we're saying the ozone level's high, higher than 0.12, the federal ozone standard. What assumption are you making concerning the distribution of X, the ozone level in the air? That's a technical assumption based on the theorems. The theorems, even with T distributions, assume the population is normal. Right? If you look in the book, chapter 8, even when the population, even when you're using T distributions, for the theorems to be true, you need a normal population. But remember, in real life, when is anything going to ever be exactly normal? Practically never. So when you're applying the theorems, you're essentially applying them approximately. We've got a population that's approximately normal. So the theorems, you might say, are approximately true. Well, that's a little funny to say. Theorems are either true or false. They can be proven or not. When you apply them, you are, in a sense, applying them in an approximate sense that you're hoping your population is close enough to normal that you can still say the conclusion is approximately true. And that's what they're after. We're making an assumption that this ozone level in the population has got a normal distribution. I said I was going to find the p-value as well, even though it's not asked for. There we go. P-value, what is it? It's the probability. I wrote this down once. I'm going to write it down again. Of observing a test statistic as extreme or more extreme as what you actually observe under the assumption that the null hypothesis is true. I'm saying test statistic, you could also probably say of observing data as extreme or more extreme as what you actually observe. The test statistic is T. There's the observed value of the test statistic. Observed value of test stat. So as far as the p-value goes here, probability of observing a test statistic, which would be from a T29 distribution, a T29 random variable, as extreme or more extreme, where as extreme or more extreme is always with respect to the direction of the null hypothesis, or the alternative hypothesis, which is right-tailed here. So I want greater than or equal to there. If it were a left-tailed test, like on the test, the exam, it would be a less than or equal to. If it's two-tailed, then if your distribution is symmetric like these are, you'd find a one-tailed p-value and you double it effectively. This is the probability we'd want to calculate. And if we want to get our best approximation we can, use technology. So go to my distributions menu again, go to TCDF. We're trying to calculate not this area, which is 0.01, but another area to the right of 2.739, which is going to be a little smaller than 0.01. That green area, that's the p-value. TCDF if I do it this way, I'm going to have to subtract the answer from 1, right? Because this is a CDF value with a less than or equal to. We're doing a greater than or equal to. Degrees of freedom is 29. That's not the p-value. You need to go 1 minus that for the p-value. This is approximately 0.005. We have observed data that occurs about 1 out of every 200 times when the null is true. Therefore, we think the null is false. We reject it. We got a p-value small, definitely smaller than alpha. We can definitely say this is statistically significant at the 1% level. Remember, p-value is not the probability that the null hypothesis is true. Maybe many people want to think that. Maybe many people want to think, oh, that's small. It's a very small probability that the null hypothesis is true. No, that's not what it represents. You might say it doesn't hurt to pretend it represents that, but don't pretend. It's always good to remind yourself that nobody can figure out the probability that the null hypothesis is true. It's an unanswerable question. It's not even a well-defined probability question, okay? This is the probability of observing data and test statistics as extreme or more extreme as what we actually observed if we assume the null is true. We have observed something rare if the null is true. Since it's so rare, when the null is true, we say the null is false. Is it a guarantee the null is false? No. We might have, the null might be true and we just observed something rare. We might make a type 1 error, but there's a small probability that we made a type 1 error. Lots of ideas, lots of terms, lots of calculations sort of go all swirling around in your mind, right? That's what it feels like. Just got to keep going here, okay? Let's go on to proportions now. Again, we did talk about proportions some last Thursday. We did this problem, confidence interval for a proportion. I did allude to the fact that there's also a formula for figuring out sample sizes. When you want a certain margin of error, there's a couple formulas, in fact, for that are commonly used. There's this formula right here. Take the sample size n to be approximately this quantity, where d represents the margin of error you desire for a proportion, maybe 0.01, for example. D could be 0.01. Z represents a critical Z value based on an alpha that you're given. So for example, if you're after a 95% confidence interval, think with me here, 95% confidence interval, alpha is 0.05. Z sub 0.025 is our old friend, 1.96. You'd square that. What's the p hat here? That's a prior estimate of p. In this example, they assume the prior estimate's 0.91. This is very rough, okay? How do you know this prior estimate's any good? Maybe you're somewhat confident in it. It's giving a very rough approximation, you might say. And by the way, you should always round up. If when you plug the numbers in, you get a number like 422.1, should really round the answer up to 423. To play it a little safer, doesn't hurt. Does that happen in this example? I don't know. I didn't plug this in my calculator. I suppose you could. 1.96 squared times 0.91 times 0.09 divided by 0.01 squared Okay, it does happen. And yeah, they did round up 3147. If you want to play it extra safe, extra conservative, it never hurts to use the formula on the next page, which is a simpler formula. No p hat in there. This will give you a bigger value of n than the formula on the previous page. But hey, bigger is better as far as playing it safe with your margin of error. These formulas are actually related, though they don't look like they are related necessarily. You can get from this one to this one by replacing p hat with 0.5, right? Because 0.5 times 1 minus 0.5 is going to be 0.25, 1/4. And that's where the 4 comes from. Effectively, this, if you think of this as a function of p hat, this function is maximized a la calculus when p hat is 0.5. So if you just always assume your prior estimate is 0.5, you're making this as big as possible, and you might as well just use this formula, which makes n bigger if you want to play it safe. Is that a good idea? Always? Bigger samples are more expensive, time and money. So your boss may not like it. Right? The boss might say, oh, I don't want to do a sample size that big. They'll cost us an extra $1 million, an extra month of time. You know, think about doing crash tests for cars, right? That's a lot of time and money. Safety crash tests. And you're looking at the proportion of crash test dummies whose chests get penetrated by some projectile when the car's in a crash or something. That's a lot of time and money. So, yeah, I mean, in real life, people have to make real life decisions based on this stuff. And yeah, this is nice to get a guarantee, but your boss may not like it. Of course, you could also make it smaller by making d bigger. If you don't want a super small margin of error like 0.01, then go for a bigger margin of error like 0.05. But maybe that's too big to be useful. There's always trade-offs in these things. People debate these things, not only from a theoretical statistical level, but also from a practical implementation level. You can do hypothesis testing for proportions too. We started this problem last Thursday. I don't think we finished it. New computer network is being designed. The makers claim it's compatible with more than 99% of equipment already in use. Set up a null and alternative hypothesis to support the claim. We get data from a sample. We've got to calculate the p-value and make a decision. Maybe we would finish this. I'm not remembering. Let's quickly go through it again, even if we did finish it. Chapter 9, number 11. P, the population parameter, represents the proportion of these things that are compatible with existing systems or whatever it is. Equipment already in use. Again, it feels a little scary, you might say to me, to be doing an alternative hypothesis for a proportion that's a right-tailed test where the null value is so close to 1 already. This feels a little fishy. Is it valid even, you might wonder, okay? It's in the book, it's a problem. I think they still want you to use the main techniques, but when proportions get close to 0 or 1, you might wonder whether the results really are valid because, for one thing, even though binomial distributions are approximated by normals, the approximations work best when the p, the probability of success, is close to 0.5. Not so well when it's close to 0 or 1. You remember that from chapter 4, but that does happen. And these proportions are, and the count of successes are related to binomial distributions. We got a sample proportion p hat equal to x over n equal to 298 over 300, which is bigger than 0.99. Well, you might say not by much. 0.993 repeating. Is that a statistically significant value for this right-tailed test? Is it extreme enough to reject the null? It might seem like it's not. It probably is not, but I mean, what would be an extreme value? 0.999? Is that extreme enough? It's still relatively close to 0.99. Let's finish the calculation anyway. The z statistic that we compute, we do go back to z in chapter 9 with proportions instead of t. The reason we use t is really because of replacing sigma by s, population standard deviation by sample standard deviation. That's really the reason we use t in chapter 8. Take the observed statistic here, the p hat, minus the null value, p0, divided by what? Well, so far it's been either sigma over square root of n or s over square root of n. Here, in this context, it's something a bit more complicated. Square root of a p-value times 1 minus p over n. When I say p-value, I don't mean p-value for a test. I mean a proportion value. You're giving the null the benefit of the doubt. You're assuming the null is true. So you actually use the null value here as your p in this formula. If the null is true, if the population proportion really is p sub 0, this will be an approximately standard normal distribution. Call it a z. It's actually not technically exactly standard normal. For one thing, because technically z is discrete here, because p hat is discrete based on a fixed sample size and is finite, right? And p hat can only take on finitely many values, only finitely many fractions you could compute here. But it's close enough. Wave your hands. You might wonder, why don't we use some other variable like a t or something else here instead? Well, this is what people do. So here are the numbers. Is this going to be extreme or not? It's hard to tell here. It's the ratio of two small numbers, which could be big and it could be small. 0.99 times 0.01 divided by 300 is a pretty small number. In regular notation, that would be 0.000033, 4 zeros. But I'm taking the square root of that. It gets a little bit bigger. 0.00574456. The ratio in this case is going to be relatively small. About 0.58, say. But it's hard to know that until you actually do the calculation. It could have been bigger, like 2 or 3. So the p-value of the test now, because it's a right tilt test yet again, is the probability that capital Z, a standard normal random variable, is greater than or equal to 0.58. Use a normal CDF. Like this. Get an answer for the CDF value, because that's a greater than or equal to, we'll have to do 1 minus that. The p-value is about 0.28 here. Small, but not super small, not small enough to reject. Therefore, fail to reject the null. You know, it's not that somebody might come along and say, that's small enough for me, I'm going to reject the null. But if you were on the job and you rejected the null based on this p-value, you might get fired. Okay, it's not small enough to reject the null in a work type situation. So it seems like the claim should not be, the null should not be rejected. So the practical conclusion is the claim that it's compatible with more than 99% of the equipment already in use. We say that's false, actually, because we failed to reject the null. We accept the null. Should we say accept the null? People do. I say it's better to say fail to reject. We just don't have strong enough evidence against it. It's like you're the prosecutor. Still think that defendant is guilty, but I just didn't convict them. So I failed to convict. Take a stretch break. All right, let's begin again here. Let's do a two-tailed test. First time doing a two-tailed test. A battery-operated digital pressure monitor is used in calibrating pressure gauges. It's thought that 95% of the readings it gives lie within 0.01 pounds per square inch of the true reading. A series of 100 tests, that must be the sample size at 100. The gauge is subjected to a 10,000 pounds per square inch pressure. And the test is considered to be a success if the reading lies within that amount, 0.01. We want to test P equals 0.95 versus P is not equal to 0.95. When I first typed this, I could not get the not equal sign in there. At the 5% level. We want, so you just thought that 95% of the readings lie within 0.01. So the number you want to focus on there is the 95%. P is the proportion of these gauges that give readings within the desired amount. We think it's 95%, maybe based on past data, but we're wondering if it's changed perhaps. This is, you got to kind of imagine the possible settings. We're wondering if it's changed from the past. It's another common kind of situation to do hypothesis testing. But we're not sure if it has changed, and we're not sure if that change has been to make it bigger than 95% or less than 95%. I think it's not so much a prosecuting attorney kind of situation here. We don't necessarily want to disprove the null here. We're just wondering, does the evidence seem to indicate that the null is no longer true? Tracking with me here? This is a context sometimes. Sometimes it's like you're the prosecuting attorney. Sometimes it's just like you're an observer at the trial. You don't know if the defendant is innocent or guilty, and maybe you don't care one way or the other. You're just interested in trials and how they come out. And you're wondering what's going to happen. And yeah, it's this not equal to that makes this a two-tailed test. We are setting alpha to be 5%, so that's going to be the level of significance that's being preset. That is, we are deciding what the probability of a type 1 error is going to be ahead of time. Nothing about p-values here. Part A says, what are the critical points for the test? Notice they say critical points, not critical point. Because this is two-tailed, the test statistic value could be extreme in one direction or another. If we convert it to Z, it could be extreme either in the positive direction or the negative direction. So I want the overall alpha to be 0.05. That means I want the overall area under a standard normal distribution, N01, to the right of a large p-value and to the left of a small p-value to be alpha, a total of 0.05. So that means I need these areas to be alpha over 2. .025 for those areas. In other words, I need to find Z sub 0.025 and Z sub 0.975, which by symmetry is going to be the opposite, negative Z sub 0.025. This is standard normal, it's centered on 0. And that's our favorite number, right? 1.96 there. And negative 1.96. Don't even have to look it up. Those will be our two critical values for the two-tailed rejection region in this context. Critical points for the test. Those are the two answers. 1.96 and negative 1.96. As far as the rejection region goes, or critical region, it's to the right of positive 1.96 and to the left of negative 1.96. You get a test statistic in one of those two ranges, then you're going to reject the null. What do we observe for p hat? Based on your random sample of size 100, we got p hat to be 98 over 100, 0.98. So the corresponding Z, if we assume the null is true, is going to be positive in this case, bigger than 0.95 for, because p hat's bigger than 0.95. If p hat had been less than 0.95, the corresponding Z would be negative. But our p hat is 98 over 100, 0.98. So our Z is going to be a positive number. Again, if p hat had been less than 0.95, then we would get a negative number. For example, if it had been 0.92, it would be the opposite of whatever we're about to get here. You're going to get a large value of Z here. It's going to be bigger than 1. Is that large? It's hard to know for sure yet how large that is. Okay, well, not large enough to be in the rejection region. We're not going to reject the null. Therefore, we fail to reject the null for this problem. We do not have strong evidence against it. We fail to reject it. We don't have strong evidence that it has changed. It seems that if we want to give the null the benefit of the doubt, we're going to say it's still true. That 95% of these give accurate readings for the pressure. Because we fail to reject the null, we're subject to a type 2 error. Maybe it really has changed, but we haven't rejected the null. Is that good or bad? I don't know. I have to think about if you were maybe a company manufacturing these gauges. If we had gotten negative, or got 0.92 there and gotten negative 1.38, we also would have failed to reject the null. You're not asked for the p-value here, but if you had to find the p-value for the two-tailed test, you'd want to double the one-tailed p-value because of symmetry. Two times the probability that Z is greater than or equal to 1.38. It'd be the area to the right of 1.38 really plus the area to the left of negative 1.38. Would be the p-value for this test, and it's a relatively large p-value. How big is it? There's the one-tailed p-value multiplied by 2. This is about 0.1676. Small, but not outlandishly small. Don't reject them. Can you clarify anything? Two proportions. Superplasticized concrete. Ever heard of superplasticized concrete? I haven't except when I do this problem. Formed by adding chemicals to conventional concrete to make it more fluid, so it can be placed more easily. Hopefully it still hardens fine. Suppose a sample of 50 new construction projects in Dallas-Fort Worth yields 15 that are using this new type of concrete, and 60 in Boston also yields 15. Let P1 and P2 denote two proportions, one for Dallas-Fort Worth and one for Boston. For all construction in both cities that use this kind of concrete. It's a natural thing to wonder, are P1 and P2 the same or not? Is Dallas-Fort Worth different than Boston or not? That's a natural thing to want to study in this context. People, constructors in the South, different than ones in the Northeast. It says find point estimates for both P1 and P2, and also the difference, P1 minus P2. Part B, find a 95% confidence interval for P1 minus P2. And part C, would you be surprised to hear someone claim that P1 is clearly larger than P2? P1 hat is certainly larger than P2 hat. 15 out of 50 is certainly bigger than 15 out of 60. 15 out of 50 is 0.3, 30%. 15 out of 60 is 0.25, 25%. So the sample proportion for Dallas-Fort Worth is bigger than for Boston. But is that statistically significant evidence that the population proportions are different? Again, that's always the issue. By the way, here, haven't really emphasized this, but all these problems that we're doing and all this theory that we do assume random sampling. If you don't do random samples, all this stuff's out the window. I'm serious. Especially if you do clearly biased samples. Like you only pick a certain contractor in Dallas-Fort Worth and another certain contractor in Boston. And you're not sampling from all contractors in some sort of relatively random way. Is it possible to do true random sampling in practice? That can be difficult, but it's one of those things like with independence where you hope it seems reasonable. And you can try to do truly random sampling. You can do some randomization in various ways, but it can be difficult sometimes, especially surveys, because, you know, surveys, you get surveyed, email, phone, something else, you don't feel like answering. Well, because you don't feel like answering, that biases their survey. It has practical consequences for them. You may not care, but it does cause bias. Online surveys at websites, people who answer the survey are maybe more passionate about the question than people who don't care. And that means the results they're getting are not really based on random sampling. It's biased. And so all the theory and all the practice, what we were doing is kind of out the window to a degree. You can do it, but it doesn't really tell you what you might want to know. The theory is based on random sampling. I hope you could do point estimates for these things without me telling you what to do. I've said 2 of them already. Problem number is this, chapter 9, number 18. P1 hat for Dallas-Fort Worth is 15 out of 50. 0.3. P2 hat is 15 out of 60. 0.25. The natural estimator, point estimator for P1 minus P2 is, how about P1 hat minus P2 hat? 0.3 minus 0.25 is 0.05. very natural and logical. Is it an unbiased estimator? Or is this an unbiased estimate from an unbiased estimator? If you assume random sampling, yes, you can prove that. It's also technically necessary to prove that the samples are independent, at least if you want to know facts about the variance of this difference. That these samples are independent of each other from these two populations, which seems reasonable since Dallas, Fort Worth, and Boston are so far apart. Finding 95% confidence interval for the difference. In general, a level 100 times 1 minus alpha percent confidence interval to estimate P1 minus P2, a difference of two population parameters, which in and of itself could be thought of as a population parameter, is a point estimate, P1 hat minus P2 hat, plus or minus a margin of error. And the margin of error, it shouldn't be a surprise, is a Z critical value, Z sub alpha over 2, times something else. And probably that something else involves a square root like it always does. And yeah, it turns out if you assume these random samples are from two separate populations and that they're independent of each other, it turns out the thing you multiply by is a square root of a certain sum. And this is the sum of these two fractions. So what's this going to be here? It's going to be 0.05 plus or minus, what level of confidence are we after here? 95%, so our old friend comes into play, 1.96. Square root of 0.3 times 0.7 over 50 plus 0.25 times 0.75 over 60. You know, the biggest thing with these kind of problems is just not making a mistake at this point. There's the thing under the square root. This, if you want to try to get as much partial credit on an exam as possible, go ahead and write that that's 0.007325. Take its square root and multiply times 1.96. Looks like we get 0.05 plus or minus. If we round to the same number of decimal places, I'd round to 0.17. Approximately. In interval notation, 0.05 minus 0.17 is negative 0.12, 0.05 plus 0.17, 0.22. And again, I don't care if you use a closed interval or an open interval if I ask you to write it in interval notation. We're 95% confident that the true population difference, P1 minus P2, is somewhere in this interval. Would you be surprised to someone claim P1 is clearly larger than P2? You should answer no. Or, excuse me, yes, sorry. Why? I would be surprised if somebody said P1 is clearly larger than P2 because this interval contains both positive and negative numbers. You might even say it's almost, contains a lot of both positive and negative numbers. There's no clear evidence that P1 minus P2 is definitely positive or definitely negative here. Since this contains both positive and negative numbers, since this margin of error is so big compared to the point estimate, we don't have much evidence that P1 and P2 are different. And we certainly don't have much evidence that P1 is bigger than P2. Yes, P1 hat is bigger than P2 hat, but that could have happened just by chance, even if P1 and P2 are the same. We don't have much evidence that they're different. So the answer would be yes, I'm surprised if somebody says P1 is clearly larger than P2. So you are talking about population parameters there, not hats, not sample statistics. Final conic problem to do is comparing two proportions with hypothesis testing. We don't have the time to go through the calculations completely, but let's get things set up and talk about what you should do. Two types of metal detectors are used: continuous wave and pulse field wave. You know, and this book is 20 years old. I don't know how out of date this is. They're equally efficient at detecting large metal objects such as guns or knives, but the one is less efficient with small objects. You know, this is kind of like airport security. Testing these things. P1 and P2 are the proportions of passengers that pass through the continuous wave and pulse wave detectors respectively that trigger the device. Set up hypotheses to support the contention that the continuous wave is triggered more often, higher proportion than pulse wave. It's certainly happening for the sample. The continuous wave P1 hat, look at the numbers down near the bottom here, 113 out of 175, pretty big. P2 hat is only 4 out of, I guess it's still 175. P1 hat is definitely bigger than P2 hat. Based on that, probably we're going to reject the null. But what is the p-value of the test and what practical conclusion can be drawn? You do need to calculate a z statistic. And what is the formula for the z statistic in this context? Well, the hypothesis test itself, the null is that P1 equals P2. The alternative, is it one-tailed or two-tailed? It is thought that a continuous wave detector is less efficient. So that would mean it's thought that P1 is bigger than P2, because it just, I guess that means it accidentally detects things too easily. P1 is bigger than P2. It's too sensitive to small objects, I guess is what they're after here. So this sounds like a one-sided test, a right-tailed test. P1 is bigger than P2. We got to calculate a test stat and compute a p-value. What's the test stat? It's a z. It's a fraction still. The numerator is still a difference. Actually, can be thought of as a difference in two different ways. I'm serious when I say that. The ultimate formula, simplified formula, is P1 hat minus P2 hat in the numerator. But to tell you the truth, technically speaking, that should be thought of as P1 hat minus P2 hat minus something else, minus a null value for the difference P1 minus P2. However, in this kind of context, if the null is true, if P1 equals P2, that means P1 minus P2 equals 0. These are equivalent here. And the alternative would be that P1 minus P2 is bigger than 0. So what I'm trying to say is we don't have to actually write P1 minus P2 here because it's 0 if we assume the null is true. We don't have to write -0 because that doesn't affect anything. In the textbook, they do initially write this formula in this way. And notice there's a P1 minus P2 sub 0 there. But for us, and almost always when people use this test, that's 0. So they don't bother writing it. Something a little different than usual happens in the bottom of this fraction here. It still involves a square root. And you still could think of it this way, as this square root. However, that's not what's done. Hang on, we're about done. This is the formula for it. And what is that? And why are there p hats there without subscripts? That p hat there and there is called the pooled proportion. And it's got two ways it could be computed. You could think of it as x1 plus x2 over n1 plus n2, where p1 hat is x1 over n1 and p2 hat is x1 over x2 over n2. Or you could think of it as n1 p1 hat plus n2 p2 hat divided by n1 plus n2. Why in the world is this called a pooled proportion? First of all, it's called a pooled proportion because we're pooling the two samples together into one big sample. And why are we doing that? Because when we're doing the test, we're assuming the null is true. And if we assume the null is true, that P1 minus P2 is 0, in other words, that P1 equals P2, then this pooled proportion is a better estimate, logically at least, of the common value when you assume the null is true, because bigger samples are more likely to be better estimates, give better estimates. So I didn't finish the problem here, but that would be the formula you use to finish the problem. I do believe in this problem you get an extreme z statistic and a small p-value when you reject the null. I'd be very surprised if that didn't happen. All right, have a good day and a good Thanksgiving.